Hello and welcome. In this video today we are going to be talking about isomers and isomerism. By definition, an isomer is a substance, or these are substances that have the same molecular formula but different structural formulae. So they've got the same molecular formula but different structural formulae. It's very important that you know the definition as your starting point. Now we have different types of isomers. And it is important that you know the different types and when they are actually being discussed. You should be able to identify them and also to be able to give examples of the particular type of isomer. The first type that we're going to talk about is your chain isomer. So your chain isomers, what are these? These are isomers of compounds that have the same molecular formula but different types of chains. So it's the same molecular formula but different types of chains. Now what do I mean by this? What we are simply saying to you is that one, the chain could be a straight chain, or the chain could be a branched chain. So when you are talking of a chain isomer, basically you are referring to substances that belong to the same homologous series. And so a good example that we could give you to show chain isomers would be one where you've got something like pentane, whose formula, pentane, and also 2-methyl-butane. The molecular formula for pentane is C5H12, which is the same as the molecular formula for 2-methyl-butane. However, when you now look at the structures of these substances, that is where you are going to start observing the difference in their chain arrangement. So for pentane, the structural formula would be as follows. So you've got a carbon, a total of 5 carbons in the chain, 1, 2, 3, 4, 5, and around each carbon you've got your hydrogens. It is an alkane, and therefore there are no double bonds or any other atom other than your carbons and your hydrogens. And this molecule is just made up of your carbons and hydrogens. When you count, you've got 5 carbons and you've got your 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And then you've got the second substance, which is your 2-methyl-butane. Now, your 2-methyl-butane, as the name says, so the long chain would have 4 carbons. And then on carbon number 2, you will have the substitute group, which is your methyl group, the side chain. So at this point, you would have that side chain, the methyl group there. And thereafter, you can look at the formula of the substance. So this is the structural formula that you are representing. Take note This here is a straight chain, and this for 2-methylbutane is an alkane that is branched. So that is an example of your methyl, your chain isomer. A second example that you could use to show the chain isomerism would be if you have a compound such as 2,3-dimethylpentane, e.g. 2, 3, then dimethyl pentane, and then a second being an isomer with 2-methyl hexane. Now, what you want to observe in this particular scenario is that you've got, so that when you look at the structural formula, let's look at the molecular formula first of the substances. This one's got 5 carbons in the long chain, or better still, total of 6 carbons, so it's going to be C6H14, which is the same as that one, C6H14. It's C7 actually, not C6. C7. C7, H16, C7, H16. So now when you look at the formula, the structural formula of the substance, it's 2,3-dimethylpentane. The long chain has got 5 carbons, 1, 2, 3, 4, 5. And on carbon number 2 and carbon number 3, so this carbon number 1, and then on carbon number 2 and carbon number 3, you have an alkyl side chain. And on carbon number 3, you have another side chain, which is an alkyl, which is methyl in this case. And you have that. So it is also, this is a branched chain. And when you look at your 2-methylhexane, what you're going to observe, I'll just write this one blue, 2-methylhexane, so 6 carbons, 3, 4, 2, 4, 5, 6, and then on carbon number 2, you've got your methyl group. It is also branched, right? But now what is the difference? The difference is that this has got how many branches? It's got 2 branches, whilst this has got 1 branch. It is still a chain isomer of the same substances, or of the same substance with the same molecular formula. So the length or the nature of the chain doesn't really matter. It can be a simple chain, or it could be a branched chain, or you both could be branched, So you need to look at that and determine where or the difference is occurring. So this is based on the branching, and because of the nature of the branching that is there, it's also going to influence the properties of the substance. Later on, when you look at things such as the melting point, boiling point, you should be able to say something which is going to be influenced by the nature of the isomer that is being represented. So the second type of isomer that you should be aware of is what is referred to as the position isomer. Your position isomer. Number two type of isomer is your position isomer. What does this entail? Well, your position isomers are compounds with the same molecular formula. So compounds, these organic compounds with the same molecular formula, but different positions of functional, but different positions. Important that you know that, but different positions of the functional group. So different positions of the functional group or the side chain. So you need to look at the position of the functional group or the side chain. So a good example that we can give you, a simple one, e.g. but 1-ene and but 2-ene. Right. So now what can we see? First things first, both of these substances are alkenes. Both of them have got 4 carbons and both of them have got a double bond in them. So the formula is C4H8. So, and they don't have any other substances other than knowing that the functional group is going to be at a different position. So when you look at your but 1-ene, if you represent it, it means the double bond is a carbon number 1. The double bond is a carbon number 1, and then the other the other atoms, which are your hydrogens, then occupy their different respective places. Remember to count and to ensure that you count 4 atoms bonded to each carbon, or 4 bonds around each carbon, better still. And when you look at that, count the number of carbons, you should have 4, 1, 2, 3, 4. Count the number of hydrogens, you should have 8, 1, 2, 3, 4, 5, 6, 7, 8. So that is the first thing. So when you're looking at that, this is carbon number 1, and this is carbon number 2, that's number 3, and that's number 4. So your functional group, which is a double bond, is found at carbon number 1. So that is the position of the double bond. And then when you look at the second isomer, it's but 2-ene. So again, 4 carbons, but in this second example, the functional group is no longer at carbon number 1. This is carbon number 1, that's carbon number 2, that will be 3, and that's carbon number 4. You see that the functional group, which is the double bond, is now between carbon number 2 and carbon number 3, which is referred to as carbon number 2. That is where you find the double bond. So, or the functional group. So thereafter, we can add the hydrogens to complete the structure of the molecule. So count around each carbon, valency of 4 to 3, 4, and then 1, 2, 3, one more, 4, and then 1, 2, 3, 4. And count the total number of carbons. You've got 4 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. So those are the number of bonds that they are, and you observe that they are isomers. Why are they isomers? They are position isomers. But why are we able to say that? We're able to say that because the functional group is found in different positions, right? So these are position isomers because the functional group, so they're position isomers because the functional group, which is the double bond, is found at different positions in the two compounds, right? In the first one, it's at position 1, and the second one, it's at position 2. So that is why it is a position isomer. Second example about position isomers, we have substances such as Eg2, we've got substances like 2-methylpentane, 2-methylpentane, and also 3-methylpentane, right? So in this particular example, how are we going to say the functional group is the same, but what we look at now is the side chain. Which is the side chain in question now? The side chain is your methyl group. Both of these are pentanes, but the side chain is at different positions. So this has got a total of C6H14, right? So when you look at the structure of the 2-methylpentane, it will have a chain of 5 carbons, 1, 2, 3, 4, 5 carbons, and then it's got a side chain at carbon number 2. So that's carbon number 1. Let's number our carbons: number 1, number 2, number 3, number 4, number 5. At carbon number 2, we have the side chain, which is a methyl group. So there is the side chain, which is the methyl group at carbon number 2. And then the rest of the molecule is as follows. Add all the hydrogens in the appropriate spaces. And then when you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 hydrogens, 6 carbons, and that is the structure of the 2-methylpentane. We then do the same for the structure of 3-methylpentane. So the only difference now is that the side chain is now no longer going to be at carbon number 2, but it shifts position and it occupies carbon number 3. That's where the substitute group is going to be, or the side chain. So 5 carbons, 1, 2, 3, 4, 5. This is carbon number 1, number 2, number 3, number 4, and that's number 5. And then on carbon number 3, that's where you've got your methyl group. And then on carbon number 1, you've got your H groups. And on carbon number 2, must be tetravalent. Count all the hydrogens that can go there. Number 4, number 5, right? And then you count the total number of carbons, 1, 2, 3, 4, 5, 6, and then number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Again, what you observe is that the molecular formula is still the same. However, the side chain has now shifted positions. First it was at position number 2, now it is at position number 3. So when you look at the position of that side chain, so initially it's there, and now it is in a different position, carbon number 3. So that is what you need to be able to observe, right? And then the next example that we are going to talk about is the example of something like your pentanol, and I'm going to use two isomers, pentan 1-ol and then pentan 2-ol, right? So let's just have a look at that structure. EG3, pentan, 1-ol, and then pentan 2-ol, right? So the formula would be your C5H11, and then your oxygen. And then, so what you're going to, when we draw the structure, so you've got your 5 carbons, and then on carbon number 1, that's where you're going to have the functional group. So we have our functional group here. It should be H12, I think. So count your hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then the oxygen, and then you've got that. So this is carbon number 1, closest to the functional group. So that's 2, 3, 4, 5. So this is your carbon number 1. And this is the structural formula of your pentan 1-ol. And then in the other one, you've got your pentan 2-ol. So what's going to shift is the position of the functional group. It's no longer going to be at position 1, but it's now going to be at position 2. So it looks something like this. So carbon number 1, you've got your normal hydrogens. At carbon number 2, you are going to have your OH, your functional group, and then at carbon number 3, you'll have your hydrogens as normal. At carbon number 4, your hydrogens. Carbon number 5, hydrogens, and then carbon number 5, all your hydrogens. So again, when you look, this is carbon number 1, number 2, 3, 4, 5. So the total number, the only thing that has changed is the position of that functional group. So the position of the functional group has changed from carbon number 1 to carbon number 2. So those are examples of your position isomers. We have another example of a certain type of isomer, the third type of isomer type that you must know and you need to learn. So that third one is a functional isomer. So now what is a functional isomer? A functional isomer or functional isomers, these are compounds with the same molecular formula. So all of them have the same molecular formula, right? But different functional groups. But different functional groups. So you need to look and say, okay, fine, how can they have the same molecular formula but different functional groups? I will show you typical examples. The first example is something like propanol and propanone. So first thing when you look at it, this propanol is an aldehyde. And when you look at propanone, this is a ketone. So first things first, they belong to two different homologous series. So when you look at the chemical formula or the structural formula of propanol, it's got 3 carbons, and then on the terminal carbon, that's where you'll find the carbonyl group, which is your carbonyl group C double bond, and then it's bonded to an H at the end, and thereafter you've got the carbons at each at each carbon you'll have your hydrogens. And then with the propanone, same number of carbons, right? But now the functional group is no longer at the end. The functional group is now at position 2. You may want to think that this is an example of a position isomer. The answer is not the same. Your aldehyde is terminal. It will always be terminal. It's got a carbonyl group and then a hydrogen at the end, whilst this has got the carbonyl group, but next to it there must be an alkyl chain. So that is why we are saying to you that they are going to be different. So with the change in position, there's also a change in the functional group. So in this case, that is what we end up having. So when you write the chemical formula, so it is C, 1, 2, 3, there are 3 carbons, and how many hydrogens? 1, 2, 3, 4, 5, 6, H6, and then your oxygen. So even here when you count, you've got your C, 3 carbons, and then 1, 2, 3, 4, 5, 6, H6, and then an oxygen. Same formula, but different structural arrangement. So what is important that you need to make sure you are aware of when you are looking at this is that whilst the position, the position of the carbonyl group, position of the carbonyl group changes. In the process, what happens of change, a different homologous series is created. So in other words, initially you could be talking of an aldehyde, but then when you change the position, what you're now getting is a ketone. Right? Is created, hence the reason it is a functional isomer. So important. Another example that you should be aware of that you need to study regards functional isomers are esters, right? E.g. esters and carboxylic acids. These are functional isomers. So whenever you look for an isomer of an ester, you must look for a carboxylic acid which has got the same number of carbons, and that will give you the appropriate isomer. So, e.g., if I have methyl ethanoate and the other one would be propanoic acid. So how do I know? When you look at this methyl, so the methyl group has got one carbon, and then ethanoate's got 2 carbons. So this must be a carboxylic acid with 3 carbons. So this is going to be C. How many carbons? C3. And then how many oxygens? They're going to be 2 oxygens and 6 hydrogens. So even here, it's going to be C3H6O2. And when you look at the structural formulae of your methyl ethanoate, it's going to be there's a carbon and then there's another carbon. But when you are writing the structural formula of the methyl ethanoate, you are going to have, so here is your methyl group, and then your ethanoate group is here. So you've got your methyl and then your ethanoate, and then total of 3 carbons, 6 hydrogens, and 2 oxygens. So your propanoic acid, on the other hand, is going to have your 3 carbons, right? And then you are going to have that formula to represent all the atoms that are participating in the bond. Count the number of carbons: 3 carbons, 6 hydrogens, and 2 oxygens. That is what you need. So, and as an exam tip, in conclusion, what you must bear in mind whenever you are preparing for your exam, right? So this is just a simple exam tip. You must, if asked to identify isomer of a carboxylic acid, all you have to do is to look for ester. Look for an ester. So carboxylic acid, you look for an ester with the same number of carbons. The other atoms that are there are going to balance out on their own, right? And then secondly, if asked to identify functional group or functional isomer of an aldehyde, you just simply look for a ketone with the same number of carbons. Right, I hope you liked this video. It made sense. And if you've got comments, please do not hesitate to send us your comments. Like, share, and please subscribe to our channel. Thank you very much. Catch you in the next one.